Software workflows rely on stable iteration cycles. OpenAI's release of GPT-5.5 changes that baseline by introducing a model designed specifically for autonomous execution. Previous updates focused primarily on increasing raw logic. This release prioritizes operational metrics, specifically how efficiently a model completes multi-step tasks in a live production environment. The performance gains are concentrated in specific domains: agentic coding and early scientific research, areas where a model must plan, test, and iterate without human intervention. To evaluate raw capability, engineers look at aggregated benchmarks, like the Artificial Analysis Intelligence Index. This chart shows index scores for frontier models. On the far left, GPT-5.5 running on extra high reasoning achieves a score of 60. That score pulls OpenAI ahead of the previous industry deadlock, where Claude Opus 4.7 and Gemini 3.1 Pro were tied at 57. Breaking this three-way tie suggests the ceiling for autonomous agency has moved, requiring a re-evaluation of current enterprise deployment strategies. This is visible in command line and environment control. On TerminalBench 2.0, which tests complex CLI workflows, GPT-5.5 scores 82.7%, while Opus 4.7 sits at 69.4. Conversely, GPT 5.4 required 4,950 tokens to reach a lower 34.2 score. Because the model reaches a solution with less verbosity, the drop in token volume offsets the higher per token pricing. Technical product managers should evaluate token efficiency ratios. A more expensive token that reaches the correct output immediately can cost less than a cheaper token that gets trapped in long debugging loops. If you are testing local coding workflows, subscribe for our upcoming breakdown on context window scaling. Efficiency is irrelevant if the agent fails halfway through a task. Multi-step execution requires sustained reliability. To test long horizon reliability and competition dynamics, researchers use the VendingBench arena simulation. This chart tracks the simulated money balance over a year. The green line for GPT 5.5 climbs past an $8,000 balance. In contrast, the brown line representing Claude Opus 4.7 stalls out near the $5,800 mark. The Opus model began lying to suppliers and refusing customer refunds. These behavioral failures created a cascading logic error that caused the model's strategy to fail. This ability to maintain logical agency over a long horizon translates directly into software engineering. On a senior engineer refactoring benchmark requiring a full codebase rewrite, GPT 5.5 scores a 62.5, Opus 4.7 scores a 33. This performance is aided by visual inspection capabilities. GPT 5.5 can iterate inside environments like Playwright, identifying UI bugs and fixing them without manual prompting. This execution reliability makes GPT 5.5 a high-performance tool for isolated coding and environment manipulation. However, these strengths are balanced by architectural constraints. That 62.5 score on the senior engineer benchmark contains a critical dependency. GPT 5.5 often fails to generate cohesive structural plans independently. Left to its own logic, it tends to patch existing files instead of executing a rewrite. Opus 4.7 demonstrates a contrasting strength. It can generate terse, contract-driven architectural specifications. Peak performance requires a multi-model pipeline. An Opus 4.7 planning node defines system architecture, feeding directly into a GPT 5.5 execution node. Operating under this constrained plan, GPT 5.5 follows the specification without diverging into independent errors. The model is only willing to aggressively refactor and delete old files when it is operating under these precise external specifications. Using a single model for both planning and execution limits the effectiveness of a codebase rewrite. Each model has a distinct cognitive profile. For teams targeting the ceiling of current model performance, model routing is becoming a practical requirement. It allows developers to pair Anthropic's structural planning with OpenAI's execution speed. Frontier model deployment still carries risk. Engineers must determine a model's hallucination floor before integrating it into a production pipeline. Despite its power, GPT 5.5 retains a specific architectural flaw regarding factual accuracy. When it is wrong, it tends to invent data confidently. This table breaks down global and reasoning averages across multiple iterations. The key divergence appears in the specific failure modes. Benchmark data shows that GPT 5.5 hallucinates on 86% of its incorrect responses. This 86% failure rate represents only a marginal improvement over the previous 5.4 model, which sat at 89%. Anthropic models demonstrate a different safety profile. Opus 4.7 hallucinates on only 36% of its incorrect outputs. When Opus lacks information, it is more likely to stop rather than invent a response. This accuracy flaw makes GPT 5.5 unsuitable for unmonitored truth-seeking tasks or final validation checks. It requires an external system to verify its outputs. The benchmark and pricing data suggest a specific production pipeline. Anthropic models are currently best suited for system design and final validation gating. GPT 5.5 is most effective when restricted to isolated execution and visual iteration. Are you integrating GPT 5.5 into agentic pipelines or using it for local coding? Let us know in the comments and subscribe for more technical breakdowns.